Finally, we're here on the last uh, topic of chapter 11, representation of function as power series. And last time we kind of glanced over the idea of how you calculate the convergency interval and radius of convergence uh, for power series. Now today we're going to say, okay, if we have a representation of a function for those series, can we kind of uh, mention at least some of those representations? Okay, this is something that I kind of proved it last time. Mentioned that if we have x to power n summation of x to power n, then this series is convergent if x is chosen less than 1 and divergence otherwise. By the way, if x is -1, it's still divergent. It's alternating, but in terms of the series do not decrease. So this is a strictly less than 1. So this is a convergent series if x is strictly less than 1. And what is that series? That series is 1 plus x squared plus x cubed, and this is exactly the same as 1 over 1 minus x. This is what I kind of proved last time. So the function 1 over 1 minus x over the interval -1 to 1 could be basically written as the sum of these uh, x to the power n powers. It could have been represented as this power series. Okay, we can kind of use this to express other uh, functions as sum of a power series. For example, let's look at 1 over 1 plus x squared. If we have f of x as 1 over 1 plus x squared, can we write f as a power series? So first thing that you should notice always is try to use this summation because we haven't learned anything else besides this. So I'm going to try to use this summation and recreate that function. So if you look at this summation, what we have is 1 over 1 minus x is basically 1 plus x squared and so on. This is the same as the sigma n from 0 to infinity x to the power n, right? So now if I change x, if we let x to be something like, let me say, negative x or positive x or negative x squared, negative y squared, let me do this. Then what do we have? On the denominator, you would have 1 over 1 minus y squared, and on the right side you would get 1 plus negative y squared plus negative y squared plus dot dot dot, which is the same as summation of negative y squared, negative y squared to the power n as n approaches to 0 to infinity. Right, so basically what we can say is that summation 1 over 1 plus y squared could be written as 1 minus y squared plus 1 y to the power 4 minus y to the power 6 plus so on. This is exactly the same as negative 1 to the power n y to the power 2n as n approaches from 0 to n from 0 to infinity. So what can I say about this function? This is exactly the same as that. Instead of x, we have y. So I can say this function is exactly the same as the power series n from 0 to infinity, -1 to the power n, x to the power 2n. So we found out what is the power series representation of the function. And the interval of convergency is that this guy needs to be less than 1. That means, again, absolute value of y must be less than 1. It's the same. Okay, so this is a convergent power series if absolute value of x is less than 1. And we found the representation of that power series. Here's the representation. Okay, so we, generally speaking, when we find the first expression of these functions, you go back to this geometric series. This was a geometric series, and we found out the power series based on that summation of the geometry. Okay. Here's another example. Find the power series representation for 1 over x plus 2. Remember, if we had 1 divided by 1 minus x, this would be exactly the same as 1 plus x squared, which is the same as summation x to the power n from 0 to infinity. So now I kind of want to create this 1 over 2 plus x, right? If it was 1 over 1 plus x, what do we get? Changing x to negative x everywhere. So I'm going to get 1 minus x plus negative x squared plus dot dot dot, which is the same as summation negative x to the power n from 0 to infinity. These two are the same thing. Interchanging x to negative x, you get this new power series. This is an outcome from that. Okay, so it's kind of the same, but not exactly, because now instead of 1 here, I have 2. If I want to make that 2, what do? If I have this theory, I can write it as 1 over factor out the 2. What is left is 1 plus x over 2. Or you can write it as 1 half times 1 over 1 plus x half. So first figure out what is this power series, then multiply a 1 half to it. So I already have 1 over 1 plus x, so I need to get 1 over 1 plus x half. It means change x to x half. I'll get 1 minus x half plus negative x half, which is going to be exactly the same as summation. Instead of x, I have x half to the power n from 0 to infinity. So that now that I got that, I just need to multiply 1 half. So then what would be 1 half times 1 over 1 plus x over 2? This would be exactly 1 half times 1 minus x half plus negative x half to the power 2. And this is same as saying summation, that 1 half times negative x over 2 to the power n from 0 to infinity. You can kind of simplify this, by the way. This is the part that you would simplify. The 1 half times negative x to the power half, you can write it as negative 1 to the power n, x to the power n, and you have 2 to the power n times 2. So this is 2 to the power n plus 1, n from 0 to infinity. And here it is. This is the power series representation of 1 over, so I can say 1 over 2 plus x is exactly the same as summation n from 0 to infinity, negative 1 to the x, to the n, x to the n, and divided by 2n plus 1. And what is the convergence interval? The convergence interval, I'll update it. Here was absolute value of x less than 1. Then we changed x to negative x. So it became negative x less than 1. So then we changed negative x to x over 2. So we have negative x over 2 less than 1. And then we multiply the 1 half. That 1 half doesn't affect anything. That 1 half is just a constant. It doesn't affect the radius of convergency. So the radius of convergency still here is negative x over 2 less than 1, which is the same as saying absolute value of x is less than 2. So I can say this is convergent if absolute value of x is chosen less than 2. Okay, so this is kind of the structure of creating this power series. Okay. So this idea always is lurking around the air. How do you recreate it? You start from this very basic one, and then you continue. Okay, say how do you create 1 over 2 plus x? If it was 1 over 3 plus x, you will go the same idea. Now, we can talk about differentiation and integration of a power series. It's nothing different than generally if you deal with polynomials. So let's assume that we have a power series centered at A and has a radius of convergence. If the radius is 0, then we don't really. If the radius is 0, then we have only one number. The derivative doesn't really make sense, and the integration doesn't make sense. You would have only one number. The derivative is 0. The integration would be just a constant times x. That really is not a series. Then what is the function f defined by? Let's say the function f is defined by the power series. What we can say about the derivative of f? The derivative of f would be simply, if it's differentiable, it's going to be differentiable in the interval of convergency. Then the derivative of it would be basically take the derivative of each one of these terms. The derivative of c0, it's a constant, derivative would be 0. What is the derivative of c1x minus a? This is a constant multiplied by x minus a. Derivative of x minus a is constant, would be 0. Derivative of x is 1. So you get c1 times 1, which is basically c1. Derivative of this term, drag down the exponent, multiply by c2, so you get 2c2. Subtract 1 from the exponent, x minus a, to the power 1. And so on. Derivative of the next term, drag down the exponent, subtract 1 from the exponent, you get this. So the general form of that derivative would be, you drag down the exponent from the n, you drag it down, you get n cn, and x minus a to the power, subtract 1 from the exponent. It's just the power rule. The only thing that you need to notice that is n starts from 1 now, because the first term of the series, which was this c0, this c0, it kind of disappeared because it was a constant. So we start from n equal to 1 to infinity. Okay, so if we know the function is differentiable, then we can kind of create new functions by taking derivatives. And similarly, if you're dealing with integration is some constant plus now integral of each term. Integral of c0 would be c0x, or you can say c0x minus a. It doesn't really make any difference because that c0a will end up to be around this constant. And if you integrate every other term, add 1 to the exponent, subtract 1 from the divide by the same exponent. So x minus a to the power 2, divide by 2. So generally, what you have is the integral would be some constant plus the integration of each term. And n start from 0. Okay. This integration, maybe it's not that easy to see the way I wrote it, but if you have a function f of x like x minus 3, and I ask you what is the integral of f of x, you can say x minus 3 to the power 2 divided by 2 plus some constancy, right? So if there's an alpha here, if there's a coefficient, let's say c0 or c1, then you still have that c1 here. It's a constant. Okay, so these terms of this series are basically that. Each term, if this was plus c2 x minus 3 to the power 2, then you will get plus c2 x minus 3 to the power 3 divided by 3 plus some constancy. This constancy is always there, just the same. Okay, so this general form of the integration, you've been doing this for every term of the power series. That should be the format. Okay, so it will be more clear if we do examples. So let's look at the example. Express 1 over x minus 1 over 1 minus x to the power 2 as a power series, and then find the radius of the convergence. Okay, so first thing that we know, the only function that we know is 1 over 1 minus x, and this is 1 plus x squared plus so on, which is the same as the sigma. I keep writing that summation just because I want you to see both format of writing, and from 0 to infinity. This is the same as that, just in shortened notation, right? And if we know that the interval, the convergence is as absolute value of less than 1, then This is the radius of convergence is simply 1. Okay, now how can you relate this to that 1 over 1 minus x? Notice that if I take a derivative of 1 over 1 minus x, what do we get? The derivative would be simply derivative of the numerator, which is 0, times the denominator, 1 minus x, minus the numerator times the derivative of the denominator, which is negative 1, and divide by 1 minus x squared. And if we simplify it, you'll end up with 1 over 1 minus x squared. And so what do I notice? I notice that this is exactly the derivative of that term. So 1 minus x squared, 1 over 1 minus x squared, is the derivative of 1 over 1 minus x. Which means I can say this is the derivative of 1 plus x squared plus that derivative. Or I can say it's exactly the same as the summation of x to the power n derivative. They're the same thing. Just so you can see it, I'm going to write both formats so you can notice it. The derivative of the top one would be 0 plus 1 plus 2x plus the next term would be 3x squared. This would be a x cubed here. And so on, right? And I can say this summation, and from 0 to infinity, the derivative of them, it would be exactly the same thing. The derivative of x to the power n would be n x to the power n minus 1. And when does n start? N starts from 1, because the first derivative will give you a 0, so I don't really need to take care of that one. That one would be already gone. So then after that, if you replace n with 1, what you have is 1 times x to the power 0, which is exactly 1. If you replace n with 2, you get 2x to the power 1, that's the next term, and so on, 3x squared. So I kind of found out what is the expression of 1 over 1 minus x2 in terms of power series. It is summation n x to the power n minus 1, n from 1 to infinity. And what is the interval of convergency? Absolute value of x. Okay, so the interval of convergency is still the same, the ratio, because here it's differentiable in that interval. So it's still convergent within that interval, or the radius of the convergency is still 1. This is the radius. Okay, how about this one? The ln 1 plus x. How can we find the expression of this in terms of in terms of a power series? Again, we know only 1 over 1 minus x. After a while, you should know that this is, you can write other formats of it. So this was 1 plus x squared, which was exactly the same summation of x to the power n, and from 0 to infinity. And notice this is 1 plus x, so I'll first try to create 1 over 1 plus x. And that is exactly changing x to negative x everywhere. 1 minus x plus negative x squared plus next term, which is exactly the same as saying summation negative x instead of x to the power n, n from 0 to infinity. Or you can write it as summation negative 1 to the n, x to the n, n from 0 to infinity. It's the same thing. Okay, now, what is the relation of this term with the ln 1 over x? It turns out that if we integrate 1 over 1 plus x, what do we get? We get some constant plus ln x. Right? So this is exactly it. So I can say, okay, ln x is the integral of 1 over 1 plus x minus some constant, or you can say this is the same as some constant plus the integral of this 1 minus x plus negative x squared plus dot dot dot, or it's the same as some constant plus the integral of summation negative 1 to the n, x to the n from 0 to infinity. And if we integrate that, what we get is simply c plus the integral becomes another constant, so those two constants could be added together. This is a constant coefficient, so this negative 1 to the n, if you remember, this negative 1 to the n is a coefficient, so you just integrate x to the power n. What is the integral of x to the power n? It would be x to the power n plus 1 divided by n plus 1. But there is negative 1 to the power n in front multiplied by it. So we have this summation, n from 0 to infinity. Okay, you can ask yourself, how can I find out what is this constant c? You can check that this is the same as ln, not x, sorry, ln 1 plus x. That's what I want. So this is the same as ln 1 plus x. If they are the same, if x is 0, then they should give you the same value. What if x is 0? What do we get? We get ln 1 equals some constant plus summation of negative 1 to the n, 0 to n plus 1 divided by n plus 1. So now the good part is that term here, this is always 0. So what you have is this term is always 0. What is ln 1? ln 1 is also 0. So it tells us this constant c must be 0. So I can say, okay, this constant c should be 0. So I found out the expression for ln plus 1 plus x is exactly that, power c. Okay, this is normally how you get rid of the constant. A constant could be verified by just picking one value. Okay, so this is the expression. And what is the interval of convergency? Absolute value of x less than 1. Because this 1 over 1 plus x had absolute value of x less than 1 as a convergence rate. Okay, so the radius is simply 1. We can kind of use this to find the integration and sometimes just to approximate as well. So here another one is find the power series for tan inverse of x and then approximate tan inverse to 1 over root 2 up to 3 decimal places. Sometimes they ask you to calculate the integral, then approximate the integral. But here I wanted to see a different form of that. I think you would see examples within your homework as well. So let's try this. Find the power series for tan inverse of x. So we want to find out what is tan inverse of x in terms of some summation. This is what the question is. And the only thing that we know is, again, 1 over 1 minus x equals 1 plus x squared plus so on. And in these cases, you need to be creative and try to figure out how can I relate this tan inverse to a polynomial. If you remember, or a fraction in terms of 1 over 1 minus x, 1 plus x or something. If you remember tan inverse of x, the derivative of it was simply 1 over 1 plus x squared. So I can say that the integral of 1 over 1 plus x squared is exactly tan inverse plus some constant c plus some constant. So what do I need to figure out is first what is the power series of forms of 1 over 1 plus x squared. And we did this in the last class, I think. But if you don't remember it, I can try to do it again. So 1 over 1 plus x is instead of x, you can replace every x with negative y, and then we do so change. By the way, this is exactly the same as sigma n from 0 to infinity x to the power n. So now if we change x to negative x squared everywhere, what do you get is, instead of the denominator being negative x, you'll get negative x squared, which basically becomes x squared. So you get 1 plus negative x squared plus negative x squared, and so on, which is exactly the same as summation negative x squared to the power n, as n from 0 to infinity. You can simplify it as summation, -1 to the n, then x to the power 2n, n from 0 to infinity. Okay, so let's see what is tan inverse of x. Tan inverse of x is some constant plus the integral of this 1 over 1 plus x squared, which is some constant plus the integral of -1 to the n, summation n from 0 to infinity, -1 to the n, x to the 2n dx. I forgot the dx in the last example as well. There is dx here. I should have mentioned dx. Sorry about that. There is dx. We integrate with respect to x, nothing else. Right, so these are all having dx in front. There we go. Just to some minor issues in the notation. So summation is still there, and from 0 to infinity, ask yourself what is the integral of this term. Is a constant multiplied by x to the power 2n. So the integral of it will stay -1 to the power 2, -1 to the power n is still there. What is the integral of x to the power 2n? You add 1 to the exponent, divide by the same exponent, 2n plus 1. So I can say tan inverse of x is exactly the same as some constant plus summation n from 0 to infinity, -1 to the n, x to the power 2n plus 1, divide by 2n plus 1. And how do we find out what is c? You can let x equal to 0 to find out what is c. If x equals to 0, then what do you notice is tan inverse of 0 would be exactly 0. And then you would have c plus summation of, again, 0 to the power 2n plus 1 times 2n plus 1 divided by multiply by -1 to the power n, and this is still 0 because there is a 0. So what we know is c must be 0. So this implies that c must be 0. So I can say, okay, tan inverse of x is exactly the same as summation n from 0 to infinity, -1 to the n, x to the 2n plus 1, divide by 2n plus 1. And it is convergent if negative x squared is less than 1, or you can simply say x is less than 1. Okay, so this is the first part of the question. Okay, so now what do we need? We need to figure out what is tan inverse of uh, 1 over root 2 approximately. Turns out if you use your calculator, by the way, this number is around 0.614 or something, I believe. I don't remember the exact number, but I think it's around that. And let me change this because I want to stop faster, but let's stop it up to 2 decimal places. It's the same idea. You need to add more number if you want to have higher decimal places. That means if I want to have 2 decimal accuracy, I want the difference of s minus sn be less than 0.01. And what is s and sn? S is the convergency of the summation, because we know that now tan inverse of 1 over root 2 is exactly the same as calculating the summation of -1 to the power n. Instead of x, we have 1 over root 2, 1 over root 2 to the power 2n plus 1, and divide by 2n plus 1 as n starts from 0 to infinity. We want to find out how many terms of this series do we need to add to have the error to be less than this 0.001, the remainder to be less than 0.001. And if you remember, for the alternating series, since this is an alternating series, we just need to go up to that term an, where an is less than 0.00, sorry, then an is less than that. Then we add up all the terms from a0 up to an. If we do that, then we simply have an accurate summation. So for that, I'm going to start with a0 first, figure out what is a0, and at every step I'm going to check to see if it is less than 0.001. So a0 would be replacing 0 for n. We get -1 to the 0, multiply by 1 over root 2 to the power 1 if you replace 0, and divide by 1. This is simply 1 over root 2. Definitely greater than 0.1, so 0.01, so I have to continue. What is a1? a1 would be -1 to the power 1, 1 over root 2 to the power 3, divided by 3. So this is 1 over 3 root 2, sorry, 6 root 2. Still greater than 0.01, so I'm going to continue, figure out what is the next term. This is negative. What is a2? a2 would be -1 to the power 2, 1 over root 2 to the power 5, divided by 5. And this is 1 over 5 times 4. Right, so this is 2, 4, yeah, 10, 20. 20 root 2. Still greater than 0.01 because the denominator needs to be greater than 100 to have less than 0.0. And a3 would be, in this case, would be -1 to the power 3, 1 over root 2 to the power 4, sorry, to the power 7, divided by 7, and that is 1 over 56 root 2. Now here this term is less than 0.01. So what do I need to do is I just need to add up a0, a1, and a2, because the next term is less than 0.01, so it doesn't really affect anything. So if we add up, and so we can say tan inverse of 1 over root 2 is almost the same as adding a0 plus a1 plus a2, which is 1 over root 2 minus 1 over 6 root 2 plus 1 over 20 root 2. And if I use a calculator, let me use a calculator for a second. I have a calculator here. And what did I get? I get 0.624. So I get 0.624, I think around that. And the exact value, I believe, I can check the exact value as well, just to make sure. The exact value is 0.6154. So the exact value here is 0.6154. And you notice the difference between these two is less than 0.01. Okay. So this is our approximation of tan inverse 1 over root 2 using the power series. So it's quite a useful tool. You can do similar examples for more accurate results. Okay, so this is where I'm going to stop, and this would be the end of Calculus 2 lecture videos.